Hello and welcome to the Aries 4D Science channel. Today we have Professor Naresh Dadhich, who is a renowned cosmologist and also was the former director of the Inter-University Center for Astronomy and Astrophysics in Pune, who will tell us about his own journey through the world of cosmology and also about some of the early days of Ayuka. Welcome, Professor Naresh, to this
Thank you, Sajid.
meeting. So let us start from the beginning, from your childhood days and your earlier days in science. So will you please tell us about your background, your locality, and how you started your science career?
Well, I come from a very small village in Rajasthan, and not very far from Delhi. It's about 250, 300 kilometers. And the village which had no school, so we had to walk about 3 miles to school. And in there, my first really introduction to science was that when I was in 6th or 7th, the school had a science teacher. So far there was no science teacher. And that science teacher was one of the local persons who has done BSc and joined as a teacher in the school. His name is, he's still around very much. His name is Hariram Joshi. He was the one who introduced us to the basic tenets of science, and that is that we must ask questions. Why and how things happen. And there is a reason for whatever happens around you. And the question was that yes, we should all try to understand that reason. And broadly that defined the science, that trying to understand the reasons about things that happen around you is really the science. Then around when I was in 8th, we had a science teacher, but you see, you didn't have in the high school, secondary school which you have, there was no science specialization. And that is where my brother, who was 10 years older to me, he was in Pilani, and he said, no, you should go to Pilani school because there you should study science. And that is how I came to Pilani. And Pilani is a cosmopolitan place. It's a small town, but it has, at that time it had, apart from our high secondary school, there was a Birla Public School, then the Birla Science and Engineering and Arts College. And it has its own educational campus, which was very cosmopolitan. It is first time I really heard the languages different from Hindi and Rajasthani or Marwari, which we have. And so that was really very eye-opening. And by nature, I'm very pro to understand, trying to adopt new things. What I have is urge for newness. And so that's why for me, it was very easy and to adopt to the new ways, new languages, new people. And that was very, very interesting. Then, yes.
So will you please tell us the name of the first school you had in your village and also the school in Pilani?
Yeah, that's school. So the school in the village was Saraswati Devi High School. Now you see in Rajasthan we have these Seths, the trades people, who generally work in Calcutta and around, have a, but they in their original village, all of them have a big palatial haveli, and they also have some public utilities services like school, a common well, hospital, and so on.
Okay.
So this was one of the sets of that thing. I had started this school, and the school in Pilani was the Birla Multipurpose Higher Secondary School. So that was the school right here. And of course, after higher secondary school, you next go to the college. There was this engineering college in Pilani and science college. Well, I didn't make a grade for the engineering, so I joined the science college. And after a year of in the college there was an advertisement saying that the Rajasthan government will give a 100 rupee scholarship per month for a student to study in the non-Hindi speaking states, called the National Integration Fellows.
To promote Hindi language.
No, to promote other way around, to promote the Hindi speakers to go to the non-Hindi speaking.
Okay.
And so then you said, okay, and I got that fellowship, which was something around September. So I had to find a place where to go. The nearest place non-Hindi speaking at that time was Hisar. That was in Haryana. But at that time it was Punjab. Haryana and Punjab were together. So I went to Hisar and joined their Dayanand College, Hisar. Did my BSc there. And the college still exists. I think a year back I just happened to visit that place. It was nice to see the college still in good shape. And from there, so my brother was a professor of Hindi in Vallabh Vidyanagar, Gujarat.
Okay.
And so I went there. Of course, BSc again, I did not make a grade for physics. So I took the applied mathematics.
Okay.
Now, fortunately for applied mathematics, we had the courses which were really theoretical physics. You had a classical mechanics, electromagnetic theory, and we also had the differential geometry and general relativity. So that's a special courses. So that, in a retrospect, turned out to be right.
Yeah.
That's. Then one of my teachers in Vidyanagar was a former student of Professor V.V. Narlikar, Jayant Narlikar's father, in Banaras. Now, so he told me that Narlikar has now gone to, as a Tilak professor of applied mathematics in Pune University. So you go there. So like for me, anywhere, if somebody said you do that, I do this. I came down to Pune, and that's where I did PhD. And luckily, after a year after the PhD, I got the faculty position in maths department of Pune University. So that's my.
Okay. So you had completed your MSc before coming to Pune. You did your
Yes,
PhD only here.
yeah, that's
And then you joined Pune University as a maths in the maths department.
right.
Now, afterwards, when did IUCA start and how do you migrate to IUCA?
So see, when I joined maths department as faculty in 1971,
Oh.
and I was all alone there, interested in relativity.
Oh, Jain had all. I mean, the senior Narlikar had already retired. Or?
Selvin Narlikar, he retired. Yeah, he left us retired in 73. So 73 he moved to Bombay to live with Giant in TIFR campus. And physics department had no relativity. As a matter of fact, during that time they didn't have any theoretical physics, and it was a small department. So since Giant joined there, so then I said that, so I said I should want to have some interaction.
Yeah.
So I really used to visit every week or the weekend
to TIFR.
To TIFR. And Jayant managed to get me the train fare and all.
This was in Navy Nagar, right?
This is Navy Nagar. TIFR Navy Nagar. Yeah, but I only know TIFR Navy Nagar. Not much contact with other parts.
Okay.
And so much so that it was almost I was a part of the TIFR. People all knew about it. And then I had students in the 1980s, and I also sent them to TIFR for visits. And one of my students did the postdoc at TIFR with Ajit Kembavi.
Oh, okay.
So that's how. So then I was a part of the, so to say, the Giants group, extended group. And so all the students of Giants, so actually astrophysics people all knew. So the Ajit or Kanduk, Paddy, and all others. Plenty of, that's right. That was then it is in the late 1980s, 86, I think it's 86, there were some very fortuitous situations. You see, I started this thing, and then we said we should have an astrophysics group in maths department.
Okay.
We started something new.
Yeah.
And that was something new. But then suddenly something happened there that Jayant wanted to leave TIFR.
Oh.
So he asked me, so this was 1986, June. For the preparation of the first ICGC meeting in Goa, to be held which was held in December 1987. So there was a national organizing committee, and I was also a member of that.
Okay.
There at lunchtime, he came and told me that tell your vice chancellor that he would like to join as a professor in physics.
In Pune University.
In Pune physics department.
Yes.
And it was also the time when just before that, I also did a little bit of a midwifery job for the GMRT.
Okay.
When Govind Swarup was looking for a suitable place, and he was exploring places, so near Pune he wanted to explore place. So I was his host.
Okay.
Was to organize accommodation and vehicles, etc. So we rolled. And actually, in the GMRT's project, Govind had put in this inter-university center.
Oh, I see. Okay.
That there should be an inter-university center which should participate or use for the use of the telescope. And correspond. Then we said that you see. So then I told that why don't we start an inter-university center?
Yeah.
And so that clicked, and Professor Yespal was the UGC chairman.
Yes.
So everything fell very well. Once he got, when Giant was interested, everything fell in. So that's how.
Yeah.
So then it is 1988, February 10th, really. I was drafted as a project coordinator to
for the inter-university.
For inter-university center to help help Professor Narlikar to prepare the project report. So that project report, I think this was February. By June we were ready with the project report, and then things started.
Okay.
And ultimately, the institute was foundation was on 29th December 1988.
88. So within 2 years you did, within a year.
Well, February 88.
Yeah.
And the 29th December
1988. Oh, that's
right.
Yeah.
So that's a formally, but then of course then in 89 we started with first we did the Aditi hut was then,
okay.
Then we first started with the housing and then to the institute. So the institute building got completed in 92.
92, okay.
And we were very fortunate also to have Charles Correa as the architect, and it was really wonderful to interact with him. And he was, but for him also the Ayuka was a very special project. Yes, that's
okay. So after coming here, how many faculty members were there when you moved to Ayuka?
We moved to Ayuka. Okay, so when we started with, so I started as project coordinator, whatever they call it. Then 89 at the foundation day, I think the Giant had joined as a director on 19th July 1988. 1988. That was his 50th. His 50th birthday. Right. Okay. I had brought his appointment letter from the UGC. We were in the meeting and I stayed back for a day to get the thing there. And so that Giant, Ajit, and Shyam Chandan, they moved from TIFR
to here
in 89. June 89 or something. Okay. They were there, then I think the next person immediately to come was Rana, I think.
Rana, yeah.
Rana, and then Ranjan, and Varun came a year or two later. Okay. And then things started.
Yeah. Yes. So when did you move to Ayuka? From the beginning you were there? You moved along with the...
So I moved from 10th February 1988.
Yeah.
That's right.
Okay.
So that way I am a first employee.
First employee of Ayuka.
During the project stage.
That's right. Yeah. That's the hardest time when you have to invest a lot of time on the whole thing. I have seen your photograph in
well, that was an exciting time. Building an institute was very exciting, particularly to work with Professor Narlikar. Professor Narlikar has uncanny knack of getting best out of the people.
Oh, yeah.
Knows everybody's strength and weaknesses, and so without you knowing, or he tapes you
Yeah.
beautifully for what you are good to do. It's right. It was really wonderful.
Okay. So after coming here, you started taking students, right?
No, no, sorry. Most of my students were from Pune University.
Oh, okay, okay.
So I think we had, I think I had five PhD and MPhil students.
Okay, okay.
From here, I had only one student actually. After one or two came along, they
Yeah.
completed after I came here.
Yeah.
So it was Parampreet Singh.
Param Singh. Yeah.
And that's who joined me in some 1998 or 99, something like that. 98, I guess.
So I would like to know your transition. You said you had a applied mathematics background. From there, you came to cosmology. So how was this transition taking place, or was it already there once you started your PhD?
Well, as I told you, that I BSc, I did not make a grade for physics. That's not because that I didn't, I was bad in physics. It's because I was not good in the other two subjects, chemistry and mathematics.
Okay, okay.
So by my nature, I'm a physicist.
Physicist, yeah.
That's right.
That's
So the probably I should tell you that another man how that the real test of physics I had was in the higher secondary school in Pilani. There we had our physics teacher on K.C. Saxena, who used to teach with a lot of excitement and with enthusiasm. And that's where I really got attracted to the laws of physics and how they work and how things happen. And that's that got.
Yeah.
Then in Hisar again, I had a good teacher, one Professor S.P. Pasi, who was. So that's where, and then in coming to did applied mathematics again. I had these theoretical physics subjects. So I really continue. I really, despite my association with the maths department, I'm essentially a physicist.
Physicist, yeah.
That's right.
Okay, so now we'll move on to some of the cosmology sessions, cosmology topics, and let's start with light itself.
Yeah.
You have a very unique way of presenting light and light's velocity as a maximum possible velocity possible, because it is a massless particle and it cannot be at rest. So would you please elaborate on that, just to start with the idea of.
Yeah, maybe just a bit of a historical recount that we had classical mechanics.
Yes.
Then came electromagnetic theory, which has this constant velocity sitting in it.
Yes.
And it was not only sitting, but then it was also experimentally established as something very interesting, that there is a wave that propagates in vacuum and which has a constant velocity.
Yeah.
And that was what your electromagnetic wave and gives wireless and so where things messages could be transmitted without any material connection. That was. And this constant velocity, how does one accommodate in the classical mechanics? Because in classical mechanics, no velocity could be constant, universally constant. So this was a problem,
Yeah.
and that's where you had a. So this was 75. The Maxwell gave the electromagnetic equations, and so the best of the minds worked for about 20 years, and among them the two prominent ones were the Lorentz and Poincaré.
Yes.
And who, to their credit, they have almost discovered all the effects of the special relativity, or that is, to the effects of really if the velocity of light is constant for all observers, then what it would be. So your Lorentz contraction or slowing down of the moving clocks and all that could be done. But unfortunately for them, they did not pick up the courage enough to make the statement that velocity of light is constant for all observers. And the reason for that was that they had a great reputation as the leading scientists of the day.
Yeah.
So then they were scared, if it doesn't come out right, their whole reputation goes down the drain.
Definitely.
And the whole world will laugh at you. More famous you are, more scared you are of people laughing at you.
Yes.
In the process, they missed the due credit of discovering one of the fundamental theories of physics.
Yeah.
On the other hand, you had Einstein, young man of 26, had no academic job. He was a clerk in a patent office, comes out and makes the statement that velocity of light is constant
for everyone,
and walks away with the credit of discovering. One might ask this question: what is it? How could Einstein get this idea? And that is where it comes in, when you are really confronted with this something very basic question. You ought to think something out of the box, not in your regular. So try to forget everything which you learned.
Unlearn.
Unlearn everything, and then try to see, think afresh. So Einstein, as he claims, thought, how about riding on a light? What will happen? That is, if you move with the light, then would you see light or would you not see light? There is one basic principle we had, that so long as any two frames which are connected through a constant velocity in a straight line, then those two frames are equivalent, that any physical experiment you do, you should be able to get the same result. So Einstein said, okay, let me ride on a light, which also moves with a constant velocity in a straight line. So my frame will also be an inertial frame. The fellow who is not moving, his frame is also inertial frame. Right? The fellow who is not moving, he sees the light, or I do not.
That's not possible.
So that means there is something wrong. Because that a physical entity, physical phenomena, should be the same for both the observers who are inertial observers. Then how can you save the situation? Only the way you can save the situation, that you have to legislate that nobody should be able to travel at the velocity of light. If nobody is going to can travel with this, then that velocity should be the same for all. It's the universal. And it is this, but there is this way of doing science which is principle driven. You are asking, you are not, nobody can, you are never going to do an experiment where you can ride on a light.
Yeah.
But you are in principle, and then you draw a very profound conclusion that nobody can ride on light. This way of a thing, concept and principle driven science, that is what Einstein signified, or Einstein identified. This, so he gave us another new way of work. Now, I mean, Newton also did this thing, but Newton also had other things to go by. But here, in Einstein's case, it is very, very stark that he was totally principle driven.
Okay.
Not so much not so much driven by the experiment.
Yes.
And that is what keeps Einstein separate. And some things later he does really keeps him, puts him above everybody else.
Yes.
But your point was that I should say,
how can light be moving with the velocity?
My way of looking at how do I do. So I said that, like, Einstein asked a simple question about riding on light. In the similar way, in the same spirit, I like to ask the question that are there some universal things, concepts which are universal, or phenomena which are universal? Now you will say, what do I mean by universal? So again, very simple common sense definition that anything which is same for all and equally shared by all.
Oh, anything which is same for all and equally shared by all. Yeah.
Right. That is
universal.
That is universal. That should be
simple. Yeah.
Now you ask, do we know any such things? And obvious answers come about is space and time.
Yeah.
Space is universal, same for all.
Yeah.
Equally shared, except depending upon your size, you might occupy a little more or little less. But that's leaving that aside. Otherwise,
yes.
So is the case for time.
Time, yeah.
It moves for everybody.
Yes.
It's all right. So space and time are two universal things.
Yes.
Then next question is, if there are two things which are universal, then can they be independent? Now, for things to be independent, you have to identify a property which is true for the one and not true for the other.
Absolutely.
But then I say, if you are able to identify the property which distinguishes between them, then they are not universal. To give you a simple kind of an example, if you say. So Mahatma Buddha or Mahatma Gandhi. These are two universal symbols for all Indians.
Yes.
Right? As a matter of fact, for the entire humanity, if you want to say.
Yeah.
If they are universal, but then there should be some relation between them. So now you ask the question, what is it that is the relation between them? Then you will say that the peace and non-violence
is
the thing which connects them.
Yeah.
This is. So the question here is, if there are things, if you have any two things which are universal, then there must exist a relation, and that relation must also be universal.
Yes.
That relation is not for one person, but
it should be universal.
For universal for all, everybody. So now when you say the space and time are universal, and hence they may also be connected, must have a relation, and that relation must be universal.
Yeah.
What is it that connects space and time? It's the velocity.
Yeah.
So that velocity must be universal.
Yeah.
So it is universality of space and time demands there must exist a universal velocity in nature. Without reference to any experiment.
Yes.
A simple logic
principle
which demands it.
Yeah.
So whether this is a different story that Maxwell's electrodynamics identified that velocity with the electromagnetic wave, speed of electromagnetic wave.
Yeah.
But that comes later. So in principle, I would have said that the special relativity could have been discovered if one had argued like what this in this simple argument before Maxwell's electrodynamics.
Yes.
If that would have been, it would have been wonderful. So I said, okay, let's put, had Einstein been born in 1844, he would be 26 in 1870.
Yes.
Arguing like this as we did, he would have got the universal velocity.
Yes.
And if the velocity is universal, what should we do? The mechanics corresponding to this would have been nothing but special relativity.
That's right.
5 years later, Maxwell tells you that universal velocity is velocity of light, and then Hertz and others observe is experimental. That would be the most wonderful. That simply driven by Christian logic.
Yeah.
You make such a fundamental thing in which gets experimentally, observationally verified. But that didn't happen that way. But then, but then something similar Einstein did, and that is what. That is to say, he did something which was not required. Because here also I say that in 1870, if he has discovered special relativity,
it would have been something that nobody asked for.
Because it was not necessary there.
Yes.
It was not just this on the cave. So something, and it is, so that my thing is that we put Einstein in a different pedestal than all other great scientists, simply for this reason, that he did something which would have not been done had it not been him.
Yeah.
For a long time.
For a long time. Yeah.
That's right. So you do things, he did something much ahead of his time when it was not asked for.
Yes.
So now we are talking about the universality. The next question you could ask is that, okay, space and time, two universal things, you have bound them together with the velocity of light.
Yes.
And now since you bound space and time together, so actually now you said that no, we don't live in a three space or one time, but we live in a four-dimensional space-time.
Oh.
So there is a paradigm shift.
Yes.
From space and time to be different entities, to be space and time to be bound together. So we live in a four-dimensional space-time.
Yes.
Similarly, then you might ask the question that is there anything else which is universal?
Before going to that, let me ask you one question. When Lorentz proposed his models, I mean the Lorentz equation, he was actually saying that the velocity of light should be a constant for that to be true, right?
Yes.
Or so
no, he was discovering this thing that if there is a constant velocity,
yes,
then
these things should happen.
Then how do things should relate?
Yeah.
That's it.
So was it done after this Michelson experiment was done, or?
Oh, this was Michelson model experiment was going on. So this is Michelson model experiment was from 1890 onwards for about 7-10 years.
Yes.
And the result of you see the
what was the motivation for him to come up with this kind of a set of equation?
For whom?
Lorentz.
No, Lorentz is simple. Is this that if velocity of light is constant, then you would say, and then you ask. So what you are going to say? I have two inertial frames.
Okay.
Right. Now I say how to keep between these two inertial frames some velocity constant.
Okay. Okay.
So that will now tell you how should these two frames be connected.
Connected.
So what should be the transformation which will take one to the other, such that the velocity of light is constant for both.
Okay. Yeah.
So that is how he had discovered Lorentz discovered the transformations.
So he also did not have any motivation for doing it. It was just a mathematical curiosity. I was wondering whether he was trying to explain why this Michelson model experiment was failing. No, it was not like that.
No. This is all. So Michelson model experiment failure. Also, so in one sense, is this Michelson model experiments establish that velocity of light is constant.
Yes.
That this is right.
Yeah.
So now the Lorentz and Poincare is that this is an observational fact. Why it is constant, we don't know.
Yes.
We may not know that this is how. If it is a constant, then how to accommodate in mechanics? How do I change my mechanics? So first is that transformation connecting the two inertial frames.
Yes.
That is what the Lorentz transformation is.
Okay.
Which keeps the velocity of light constant. That's right. That's how it came.
So let us move on to general relativity now, as you wanted.
So next question was that is there anything else which is universal? So, well, something which comes close to be universal is the Newtonian gravity.
Yes.
In the sense that Newtonian gravity affects all massive particles.
Yes.
Particles which have a mass,
they all be affected by
attract each other by inverse square laws.
Yes.
That's the Newton. But so that's right. But now with the velocity of light, with the light I have, light is also a physical entity.
Yeah.
Now light, if I want to treat it as a particle and as its quantum version tells you, light could be treated as a particle with zero mass. And mass, which we will always mean as a rest mass.
Rest mass.
Because that's the only one invariant good definition.
Yes.
All other, after relativity, these very confusing terms like relative mass, that's all superfluous, more confusing. So it's rest. This has a zero mass. So if gravity, so now the question is, we must universalize the gravity. That is to say, not only for it interacts with the massive particles, but it also interacts with massless
particles. Yeah.
That's the thing. Now, so this what I am now telling you is an argument different from Einstein.
Okay.
Einstein's was question which all textbooks kind of tell you was the generalization or the completion of his completion of relativity principle.
Yes.
That why only the constant velocity, can I not have a non-constant velocity?
Yes.
And that's where you come about, that's how, of course, he uses this fact of the gravity being universal. And this is being universal, that's where your principle of equivalence comes in. That locally you can remove
it. Yeah.
But you cannot remove globally. That tells you that you cannot be done this way, but you need to have to get you a geometry to do this thing. So here I'm saying is I'm sticking to my universality concept. So we have to say that gravity must also influence the massless particle. Interact with this. But then there is a very basic fundamental problem, because any action of a force on anything is measured by change in its motion.
Yes.
If particle is acted upon by a force, the only way I can measure that, observe that, is finding in the change in its motion.
Yes.
Now the problem with the massless particle is that its velocity is not in its hand.
Yeah.
It is universal.
Yes.
As a matter of fact, if you say, it is a property of the space-time.
Yeah.
It propagates in space-time.
Constant velocity.
So you can't. So velocity cannot change. But if the force within the Newtonian framework, if force has to act on the particle, then its velocity must change.
Yes.
So we have a clear problem.
Yeah.
And that is again, I come back, when you face with this sort of thing, you should forget everything and try to think totally fresh.
Yes.
First thing it tells you is that the zero mass particle does not obey Newton's second law.
Because GMM by R square won't work.
Right. The mass into acceleration is force. Mass is zero, so
it's also
force. So there is so zero mass. So that is to say, massless particle to feel the force, because so long you found the action of a force only driven by second law.
Yes.
That is not applicable. So you have to find a new way. So that's,
Yes.
so how do you find a new way? And that's when I say that you must forget everything and only use your unadulterated, robust common sense.
Okay.
And that's, so where do you find such a, so I say, okay, my uneducated farmer in my village, I ask him this question, that look, we have this very fundamental problem in physics, and can you, in your uneducated way, can you throw some light on this?
Yes.
Some. So he has a beard like me, he teaches his beard. After a little while, he asks me a question. That no, I don't understand your question. What? You have to tell me that light or the zero mass particle should we feel gravity or should be affected by gravity. What do you want the zero mass particle to do?
Yeah.
पते की बात तो है ना.
Yeah.
Tell this. What do you want to tell? Yeah. I don't understand your action or this, but you tell me what is. So then I tell him that look, if I have some massive object, if a particle passes by this, it bends.
Yeah.
And or if it is not, then it falls on this. That's. So what we want is the light or the zero mass particle also to behave similar.
Yes.
That if it is light is passing by this,
it should bend.
Should recognize the presence of this massive object and sort of salute it, bow and bend.
Yeah.
So then he goes into slumber, and after a little while, he wakes up and with a twinkle in his eye and asks me, "Is that all what you want?" I say, my dear friend, if you give an answer to this question, it would be my name after Newton. You know? Yeah. So he said, okay, let's go to the riverside. And as you know, I come from a desert, there are no rivers there.
Yeah.
So we have to imagine you go to the riverside.
Yeah.
He picks up a branch of a tree, tosses into the water. It starts floating on the water. And then he said, look, that thing is floating on your. Yes, it floats on the water as the water is moving. He said, all right, let's walk along. Walk. After a little while, the river bends. Then he said, look, that branch is also bent.
Yeah.
I said, yes, it was floating on the water. So what water bends? River bends, it bends. Then he mischievously asked me, haven't you got the answer to your question? Dumb as I am, I said, no. He said, my dear friend, in that case, why are you wasting your time? You are no good to do anything. Better look after my cows. He said, tell me, where does your light float? I say, it floats in the space. Then where is the problem? Why can't you bend the bloody space? And that is when it occurred to me that light can, or a zero mass particle can feel gravity if gravity bends the space.
Yes.
without having to change its velocity.
Yeah.
That is what he wanted. So that gives you a new paradigm that the gravity must bend space. But space, poor fellow, is not alone now. With the universal velocity, we are already bound together.
Yes.
The space-time must bend. So the gravity could only be described as a property of a curved space-time.
Yes.
So space-time has to curve to make gravity light feel gravity.
Yes.
So I have it. I think somewhere I or a talk saying, light bends the universe, and that's thing that is there. For light to feel gravity, the universe has to bend.
Yeah.
That's the so that brought a totally a new paradigm that you have because so long far no other force made such a demand on space and time. Space-time was a fixed given.
Yeah.
In which
all these
you described, you proposed the law. So you had a Newton's law, or you had your Coulomb's law. Laws were given externally.
Yes.
You prescribed the laws. Here you have no liberty, no luxury of prescribing gravitational law. Gravitational law is determined by the geometry of space-time, geometry of curved space-time.
Yes.
So so inverse square law follows from the geometry of space-time.
Great.
So that's how this whole paradigm is shifted. And Einstein brought this new aspect that the geometry is now the language of physics, fundamental physics. So all physical laws, we all try now to understand in terms of the geometric dictionary, really. So that's.
So for massless particle, of course, the curvature of space-time would affect it.
Yes.
What about massive particles? They also get affected.
Yeah. So space-time is curved for everything. Only difference here is this, that massless particle does not feel acceleration.
Yes.
Grad phi.
Yeah.
Massive particle feels the grad phi as well as the space curvature. Where the massless particle only feels the curvature.
Okay.
So that's the thing. Now, since you put this thing, you might ask the question other way around. That we have, the gravity has these two components. One is the acceleration, grad phi. That is to say, some aspect of the space-time geometry should correspond to the grad phi. This should give rise to the grad phi.
That's right.
Then some aspect of the gravity should give rise to the space curvature.
Yeah.
And that is very important to identify this, understand this. Now, this is again a question. When you come from the Newton to Einstein, two new things you have to accommodate. One new thing was light feeling gravity.
Yes.
Another new thing is gravitational fields self-interaction. So the question here, so when we said this, so when you have, so I think we say that when we universalize, that massless particle also comes in, right? Now for the source of gravity also, what it means is, it's not only the things, matter which has a mass, but the matter which has no mass
also should be.
should also be source,
Yes.
massless. So, which in to say, to make the universal term for the thing which is applicable to all, both mass and massless particle, is the energy.
Yes.
So energy is a universal feature.
Yes.
Which you.
Yeah.
Now, if that means that energy in any form must produce gravity.
Yes. Absolutely.
Now, the gravitational field also has energy. Like the electric field has energy density as half E square.
Yes.
Gravitational field also has energy.
Yes.
So the gravitational field must also produce gravity.
Yes.
That is the self-interaction.
Yeah, self-interaction.
So that when you come to the Einstein, you have also to incorporate self-interaction. So you have two things. So gravity, the light feeling gravity was taken care by if you curve the space.
Yes.
So that part is all right. Now the question you must ask, what is it that curves the space? Would it not be great that the new thing which we have to accommodate, the self-interaction,
that curves the space.
Does the self-interaction does the curving of the space. So this is a two wonderful things. You have two new things to be accommodated. They accommodate each other, take care of each other.
Yes.
Light wants space to curve, and the self-interaction curves the space, leaving Newton's universal square law intact. So this is the, what you say, pristine elegance of general relativity.
Yes. Yeah.
Where the two new things take care of each other, leaving that. And of course, you would have also said that we would have been in problem. We could not have afforded to taper with the universe square law. Because universe square law is a general law.
Yes. Applicable to everything.
Is the conservation of flux.
Yes.
Which tells you that if you have any source of a force, whether electric or gravity or gravitational or anything, the flux across a two surface is conserved, and that conserved is refers to the conservation of the source.
Yes.
So that conservation we could not have compromised with. So anything we want to do, we have to carry the conservation of flux together. So universe square law could not have been tapered with. And so that is why the self-interaction does not taper with the inverse square law. It only introduces a new thing, that you have a space which you curve. And that is what I would strongly recommend to people who want to understand a little more about this thing. I have a little essay on this, saying that on the archives, Einstein is Newton with space curve.
Yes.
And that gives.
Yeah, we'll provide that link in the description of this video. Yeah.
So that's that. Yes.
Now the next question is, of course, gravity curves space-time.
Yes.
But Einstein had to introduce a lambda parameter in his equation to make the space stable. So what is the reason for that?
Oh, yes. So what he wanted was, so he had his equation, which was very successful in the solar system and looks observed, describing the field of a massive object. But then he also wanted to apply these equations to build a model for the universe.
Oh, okay. Just like Newton also wanted to.
Yeah, everybody wants to think big. So he wants. And at that time, so this is before that, there were no observation of Hubble and company.
Okay.
So view of the universe was static. You want to have a static sphere.
Yeah.
And then again, you want is, yes, what could be the metal distribution will be these isolated particles, so dust.
Yes.
Now, if you have a dust particle, then they will all collapse.
Yes, by gravity.
By gravity.
Yes.
How to keep them? That is where he needed some force which could check it.
Okay.
That is the force when he was provided by lambda.
Okay.
And the lambda, how did it come? That in his equation, you wrote the Einstein tensor equal to the stress tensor you have.
Yeah.
Only thing from the stress tensor you wanted that you can add anything whose divergence is zero, because the Einstein tensor is a vanishing divergence. So when you wanted a vanishing divergence, the simple question was that you can add any, like in the Newtonian framework, to a potential, you can add a constant.
Yes.
Right?
Yeah.
Because so similarly, there is a, so now when you take a curved space-time, when the geometry is curved, the derivative, relevant derivative there is not the ordinary derivative, but a derivative which also takes into account the curvature of space.
Yes.
And we call the covariant derivative.
Covariant.
So then you ask something, you can add something which is constant relative to covariant derivative. That is how that lambda was introduced. Lambda times the metric. Metric is what is a constant relative to covariant derivative. That got. So this was freely available. And so Einstein took advantage of this, and that gave this compensatory thing. And that, of course, you want to know the density of things to keep at that time whatever density you have to prescribe the same value of lambda to counteract this. So that was. So this was in a way done in a very ad hoc manner. Later on, so this was fine.
When Einstein introduced his lambda parameter, his intention was only to prevent matter from falling in and collapsing. But he never tried to give any explanation for how this kind of lambda can come in nature. He assumed that it is there.
It is there, and it is his equations admit that.
Okay.
He did this, and also thought that there can only be a static solution. But pretty soon in 1922, the Russian physicist Alexander Friedman obtained a non-static solution. In non-static solution, in the expanding solution, your metal fields, the expansion takes care of it. So you don't need a lambda anymore. So that is where then the lambda becomes superfluous.
So when this equation was brought in, did he had to assume something else for no?
So now what can we saying? So this is 1917. Einstein had this Einstein static universe.
Yes.
1922, he only obtained solved the solution for an expanding universe without lambda.
Without lambda. Okay. Yeah.
So there were no lambda needed. You have.
Yes.
And that is when the people were divided. There were some people like Eddington who fell in love with lambda, who wanted this.
Yes.
But some others would. Observation did not want. The observation did not have anything. It was not required. So that's why the lambda got thrown out. Lambda again got resurrected in a different context in 1967 by Dadhich. And
Hubble's observation came in, and then when Hubble made his observation, we found that the universe is expanding. But even before that, Feynman had said that this is...
No, the Friedman's solution is before Hubble's
observation.
Friedman as well as Lemaitre. There's the Lemaitre, the Friedman-Lemaitre
came ahead
of solution of the equations are ahead of the thing. 1929, Hubble observed. And then it fitted into this. The universe is in fact expanding. It's not static. So that's why.
But did they get the corresponding credit for that?
Yes, of course. Everybody. I think Friedman, unfortunately, presumably died early. Lemaitre, for very some strange reason, has not been. You see that in Lemaitre's case. He wrote a paper which was 26, 27, something around that time, where pre-Hubble observations. He got the evidence that the universe must be expanding, and he had a model, expanding model of the universe. He published his first thing. He published first in the French, and his translation was published in the monthly notices. That one paragraph we had. That in the translation has been omitted for some very strange reason. So there has been late there has been quite a bit of debate on this. But now everybody gives the credit to this thing. But you might have said that why couldn't have been the candidate for the Nobel Prize with the Hubble? Yes, there should have been. But Friedman presumably died before that, or something else happened. But these are those sort of things. But in 1967, his resurrection was from the point where the Dadhich said that now you have this, with the quantum mechanics, vacuum gets polarized. And for that polarization, that vacuum polarization also you should take into consideration in your Einstein equation. That should also be put on the right side. And if you compute this vacuum energy, stress tensor for vacuum energy, with certain assumptions of throwing out some infinities, this is anyway this is normalization quantum theory, because quantum theory is always full of dots with that thing, then that has that same form as the lambda. So the lambda came into this. But then there was a problem. From the quantum mechanics through you bring this in, that brings in the Planck length. Lambda from the cosmology which you have, which is, so if you take that lambda ratio of the Planck length and lambda, that has 120 orders of magnitude discrepancy. So this monumental discrepancy.
Yes.
So that is why how again lambda got beaten
out. Yeah.
by this thing. Finally, lambda comes with a thumb in 1997.
Expansion again. Dark energy.
Accelerated expansion in the universe. And that is the lambda. And lambda is the most satisfactory explanation of this. You require no dark energy. But that's a different story. Dark energy, you have to do it because you can't do anything more difficult than that. So that's okay. But I have another point. I have where I want to bring out the lambda.
Yeah.
It's on the same footing as the velocity of light. It has nothing. So that let me decouple it. It has nothing to do with gravity.
Okay.
It is a constant.
So it's a constant. Yeah.
Constant of space-time structure. So now you can get back to this thing that with the universal velocity, we have a four-dimensional space-time.
Okay.
Now and this is the space-time. Now it's this space-time I want to describe, identify its geometry when free of all forces.
Yeah.
So we want to identify or determine the state of space-time
when there is no force.
When there are no force. When there are no force, what does our classical mechanics tells me? Space is homogeneous and isotropic.
Yes.
And time is homogeneous.
Yes.
That is, free particle motion does not depend upon space and time. Okay. Right? So now I would say, so as what one generally would say, that the free space-time is a homogeneous space-time.
Yes.
Space-time is homogeneous. Yeah. Now you say, what should be its geometry? The geometry, we don't put anything, prescribe anything. We want to, draw everything from the principle. If the space-time is homogeneous, so must be its geometry.
Definitely.
Geometry must also be homogeneous. Yes. That's right. Now, geometry is characterized by Riemann curvature tensor.
Yes.
So, Riemann curvature tensor must be homogeneous.
Yes.
Right? Homogeneity means it must be constant, should be same everywhere. So, same everywhere.
Yes.
Now, constant means we are in curved space-time. A priori, we are in this thing. The relevant derivative is a covariant derivative.
Yeah.
So it should, that Riemann curvature must be covariantly constant. Its covariant derivative must be 0.
Yes.
Then you say that if that is the case, then I should be able to write Riemann tensor in terms of something which is constant relative to covariant derivative.
Absolutely.
And we have talked a little while earlier that thing which is constant relative to covariant derivative is the metric. Metric Gij or G mu, whatever you call.
Yeah.
So you write your Riemann tensor in terms of G mu, respecting its symmetry properties.
Yes.
And since G mu's are dimensionless, curvature should have 1 over length square. So you should have some constant which is 1 over length square.
Yes.
And that is lambda.
Lambda.
So arrives as a, so it is, so free space time is space time of constant curvature, not necessarily of zero curvature.
Oh, okay.
Zero curvature is a particular solution.
Yeah.
So zero curvature is admitted, but the general solution is
a constant curvature.
Constant curvature.
Interesting.
That is, so this, and here it is a homogeneous space-time. So lambda comes as a constant of space-time structure without reference to any force, because it is it characterizes the geometry of a homogeneous space-time.
Yeah.
And homogeneous space-time has no physical dynamics. So it has nothing to do with gravity per se. And now you would say is that this is on the same footing as the velocity of light. Velocity of light came by universality of space and time. This thing. Now we say that if the space-time is this comes as a geometry of a homogeneous space-time. This really gives you that determines the state of homogeneous space-time.
Yeah.
And that is what is a constant curvature. Unfortunately, your textbook tell you, you say when the space, when the gravity is present, space-time is curved. Riemann curvature is non-zero.
Yes.
When there is no gravity,
it's flat.
You say space-time is flat. Riemann curvature is zero.
Zero. Yeah.
Now, in this case, situation, in this viewpoint, there is one very paradoxical situation comes. That you have a homogeneous space-time.
Yes.
Yet, it has a dynamics according to you. Because you said, the dynamics in the sense you said that the curvature is non-zero, that means there is a gravity present. So here you have the space-time is homogeneous, and you say there is a gravitational dynamics. So this is on the other hand, you have a situation where the homogeneous space-time has a constant curvature. It is not exactly, but you should take it's something analogous to you have in Newtonian framework you have a phi is constant, but nothing prescribes phi to be zero.
Yes.
The constant, the potential to be zero. Potential is a constant.
Yes.
Similarly, if the curvature is the measure of the dynamics of gravity, constant curvature is equivalent to saying constant potential. You don't have to say zero. What it tells you, constant potential, the constant curvature tells you absence of gravity. There is zero gravity. But it doesn't have. And the difference between why the things are different here when I say constant potential, I had the luxury of a fixed given space-time to me.
Yes.
So all the rest of the physics, when you have the constant potential as no dynamics, it simply said that the space-time was fixed to it.
Yes.
But we now inherently do not have that luxury of a fixed space-time.
Yeah.
So space-time has to
curve.
have a curve. Now you can say this curved space-time, you can say when it is homogeneous and when it is inhomogeneous. So the constant curvature is there. The next question immediately will come is, this is all fine you got. So first thing, I also have an essay saying two constant of space-time curvature, the space-time structure.
Yeah.
So these are the two most fundamental universal constants, because no other constant has such a degree of fundamentalness. We will refer to one little later.
Yeah, we'll add that also in the
something. But so here this is what you. So this is it's a constant of space-time structure. Now the next question you should ask. We started with the universality of space-time. We came to four-dimensional space-time. Then we wanted to characterize it when it is free of the dynamics, right?
Yeah.
Now you say, and that is a constant curvature.
Yes.
Now you ask to say, when the space-time is inhomogeneous, that is a curvature is not constant, then what happens?
Yeah.
Well, inhomogeneity, again your classical mechanics tells you, inhomogeneity indicates presence of a force.
Yes.
Presence of a dynamic.
Yeah.
So now, if there is presence of a force, you now might ask, so then what is its dynamics? And again, my question is, its dynamics has also to come from space-time curvature.
Yes.
We don't have nothing in our hand.
Yeah.
Go by. So I have a Riemann curvature. Is there anything else do I know about Riemann curvature? The differential geometry tells me that it's Bianchi derivative, that is anti-symmetrized derivative, is identically zero.
Okay.
Now this is something, so this is one of the fundamental theorems of differential geometry. In other words, say d square is identically zero.
Oh.
D representing a derivative, and a double derivative is identically zero.
Yeah.
Now first let us see, do we know that some examples of d square equal to zero? And the answer to that is yes. We know them without realizing they are d square. So we all know curl of a gradient is zero.
Zero. Yeah.
Divergence of a curl is zero. The Bianchi derivative is a higher order, next order cousin of these two.
Okay.
So the Bianchi derivative is anti-symmetrized covariant derivative of Riemann tensor is identically zero. D square equal to zero. The great John Wheeler famously said, it represents boundary of a boundary zero. It represents a conservation law. So that's you have a boundary and you take this boundary, that you will have a zero.
Yes.
So that's the so now I have the Bianchi identity, which the differential geometry gives without any.
Yes.
Now, if you have any tensor equation, you can play with it. Take its trace.
Yes.
And when you take a trace, something very interesting happens. It gives you a second rank symmetric tensor with vanishing divergence.
Okay.
W.
Yeah.
What is the second rank symmetric tensor made up of? Second rank symmetric tensor actually all made up of the Riemann tensor. You have a Riemann, its first contraction gives you Ricci.
Yes.
The second rank symmetric tensor is a combination of Ricci and Ricci scalar.
Okay.
It's Ricci minus 1/2 times Ricci scalar.
Okay.
Called the Einstein tensor.
Yeah.
It's an Einstein tensor. Its divergence is 0. So this is what is purely differential geometry given.
Yeah.
Then in my very simple farmer's way, let me integrate this.
Okay.
So I have a second rank symmetric tensor. I write this equal to some constant times another second rank symmetric tensor. Demand that is divergence is 0.
Okay.
Plus I add something which is constant relative to covariant derivative. Because the divergence must vanish.
Yeah.
So comes lambda times metric.
Yeah.
So this I got the Einstein tensor equal to kappa Tik plus lambda gik. This is the equation I have.
Okay.
Up so far we have not added anything from outside.
Yes.
Purely driven by
the space-time
thing. Tik, the new tensor which I put is only condition it is automatic by demand it has been conserved.
Yes.
Its divergence is 0. Now let us try to say, can we make a sense of this equation? So on the left hand I said I have Einstein tensor.
Yes.
Which is a creature of Riemann.
Yes.
What does Riemann consist of? It consists of second derivative and the square of the first derivative of the metric.
Yes.
So moment you have this, so on the left hand side I have a second order differential operator.
Yes.
Which is the analog of del square phi. Moment you say del square phi, then I should be able to identify something like a rho on the right. Then it becomes equation of equation of motion.
That's right.
So no, lambda is a constant, so that there is no equation. The new tensor which I have given TAB, this is a tensor who is responsible for making the space-time inhomogeneous.
Yes.
And it is inhomogeneous for everybody, universally inhomogeneous for all particles.
Yes.
That means the TAB should also be some physical property
of the
which is universal, which is shared by everything which physically exists.
Yes.
That is uniquely energy momentum.
Yes.
Moment I identify with the energy momentum. It's Einstein equation. It's Einstein gravity.
Yes.
And look, our journey was, we were nowhere asking for a theory of gravity. We were just trying to see, first started space and time, then their universality led us to space-time, then we said I have a space-time, or if I have a free space-time, then what should be its geometry? It came to the constant curvature. Then we said that if it is not constant curvature, it is inhomogeneous, then what happened? And so comes, so it's the inhomogeneity of space-time gives you Einstein gravity. Right.
Okay. Now,
so this is what.
Yes.
The whole story is so well knit and so very beautiful and elegant. Yeah.
Now there are different models. This lambda CDM model and also the dark energy related things. All these things are just spun out from the general relativity, or are they just introduced to explain experiment things in a?
No, they were, of course, these were all things came by the observation, because the whole thing is triggered by this supernova observation, where contrary to your expectation, the expansion of the universe, rather than decelerating, it's accelerating. So there is this. So here I would like to say that if one has followed this line of argument which I say, where the lambda is a constant of space-time structure, and if we have taken it seriously, the accelerated expansion of the universe should have been a prediction. Rather, we all getting baffled
by it.
Because if you had taken this, then you would have said, sometime in the future,
it will accelerate.
It will accelerate. Lambda will dominate over. Then it will accelerate.
Yes.
So as a matter of, I also say that had Einstein followed this line of argument, he would have realized that lambda is a true constant of space-time structure.
Yes.
And then he would have said, he would have probably made one of the most remarkable prediction of all times, that the universe will be accelerating sometime in future.
Yeah.
He wouldn't have been around by then, but still we would have again saluted this man. But this did not happen. Yes. Unfortunately, he left us with this great confusion, which still continues over 100 years.
Yes.
So that's then that once you have, then the people start building models. You have. So far, I think the observations beautifully fit lambda. And of course, any observation like this, nothing is totally perfect. It is always this thing. Yeah. But on the other hand, people have gone to the other end. They've started building models. Almost every day, some half a dozen models come out. And then, and it's a simple model. So you say simple trick is you have introduce a scalar field. Poor scalar field is everybody is mistress. And we put in and presumes and prescribe some potential and then try to fit in the curves. You people. That's what you have. But another thing with is that the people even went up to the extent of introducing phantom fields. Fields whose kinetic energy is negative.
Kinetic energy is negative?
Negative.
Oh, okay.
Imagine in a good old days when we were...
Are they tachyons or something?
No, this is even worse than tachyon.
Oh.
So tachyon has some general principle which follows that the velocity of light is still invariant. So it's how could we this? But these are different times when there is no premium for being stupidly bold. And people have been doing, and very, very, very famous people have been working on this, and every day. But we know that nothing there so far. They have not come up with anything that beats lambda. Lambda is still.
So one final question: is this Big Bang a necessity of general relativity, or is it just because of the expansion we are extrapolating, just as we go to absolute zero, you say that everything is at rest at that time.
So the Big Bang is predicted by the Friedman-Robertson-Walker expanding model. And this model is a solution of the general relativity.
Yes.
Einstein equation.
Yes.
So which tells you that if I go back in time, you will have a density becoming infinite. And then you build up a picture of a hot Big Bang and how the thermodynamics evolves, all those. And then somewhere you also need an inflation to make that causal connection with all that is there in the universe.
So there have been several attempts to get rid of this inflation and the singularity. Are they logically
no. Singularity is an open question we don't understand. So as a matter of fact, to me it's more related thing. Inflation I cannot. Inflation is more phenomenologically motivated. There is no physical principle which gives you. It's a phenomenology which tells you that to have a connection between them, something ought to be done. So that's where you have. So there is not where the singularity is an essential part of general relativity, as predicted by Hawking and Penrose.
Yes.
And so what it means is that what it tells you essentially identifies is the general relativity is not a complete theory. No theory will be a complete theory. So you ought to be so you have to worry about quantum gravity, and one doesn't know how quantum gravity and quantum gravity in itself is a very, very involved thing. That's the reason for last more than 50 years people have been breaking their heads, best of the people in the world. And the problem is very formidable for simple reason. The two things are very different. One has a inherently discrete structure, quantum. Other has inherently a continuous structure. Space-time geometry, curvature. And how to merge the two. So in this thing, let me get back to my universality. And we said that space-time and gravity. Is there anything else which still is universal, but which are not been synthesized with space-time? And there is this Planck's constant. Planck's constant is universal because it is applies to everything. It's a mechanics. But unfortunately, so far, we have not been able to synthesize, because since it is universal, it has to be related to everything else which is universal. Everything else we have got into the space-time. So long as we do not synthesize Planck's constant into the space-time structure, quantum mechanics will remain incomplete. And that would also mean gravities will also remain incomplete. Because you see that quantum structure of space-time will also be required for the quantum gravity. So all these questions are inherently related, not only related, are inseparable. Quantum gravity, quantum theory of space-time, and the synthesis of space-time, quantum or the synthesis of Planck constant with space-time.
Space-time. Yeah.
That's right.
So we see this singularity within the black hole and also at the Big Bang. But for the black hole, we have an event horizon which remains.
Right.
And there is no problem with the singularity because we do not need an inflation there. Or is there?
No, we don't need inflation, and there you have a singularity is always hidden inside event horizon.
Yeah. So something like that can happen in the Big Bang also?
No. The Big Bang, yeah, what is really really happened is this. Yeah, this is one of the thing with George Ellis and these two students, Roy Martins and this other fellow's name, yeah, was this, that they took a space-time distribution, density distribution at one particular event.
Okay.
And followed them, followed them back.
Okay.
Back.
Yeah.
That's right. And it converges into a singularity.
Singularity.
Yes,
Yeah.
That's that. So you have a kind of an so you don't have an horizon. So in another way, you have horizon in future for the cosmology.
Cosmology.
Cosmological horizon.
Yes. Yes.
You don't have a this
initial.
And here is on the of course it depends once in collapse it is in the future for the they are also here in this. So that's the difference.
Okay. Right. Thank you, Professor.
Oh, lovely! It's lovely. It's always it's wonderful to chat to you. And I must say, you are one of the few guys who always keep me thinking, because you always ask some questions.
Some stupid questions always have.
Well, to make me think the question has to be stupid. Thank you. Thank you.
Thank you very much.
Thank you. Yeah.